So our first speaker is Yassine Eben from Siemens EDA. He's spoken many times before for us here, so welcome back, Yassine. He's a senior applications engineer at Siemens. He's going to talk about methodology for increasing continuous integration throughput. As I said, he's a senior applications engineer at Siemens EDA with over 20 years experience in the EDA software technical account management, technical marketing, and helping guiding for customers through hands-on product evaluations and deployments. Yassine holds bachelor's and master's degrees in electronics and computing from the Institute of National Polytechnic in Toulouse, France. He's now based in the UK. So over to you, please, Yassine. Thank you.
Thank you. Thanks, Mike. Thanks, Sarah, for organizing DVClub. So today I'm going to talk about auto checks, automatic verification checks, and I'm going to propose a methodology for including these in a continuous integration flow. So here's the agenda that I've come up with. First, I want to introduce the idea of using formal technologies, so model checking, property verification for RTL inspection. I'm going to talk about some considerations for automating these so that they can run as a regular daily or weekly job. So through that, I'm going to talk about some techniques for coming up with tests that maximize the throughput of continuous integration flows. So I'll touch on things like how you create sanity tests, deep tests, SOAP targeted tests based on formal linting and formal checks. In Siemens, we've got a technology that helps you come up with these. They're called KNRW, and I'll come to that later. And then I'm going to show you how you can integrate all of this into a CI flow. Jenkins is popular, so I'm going to use it as an example for building an interface. And I'm going to finish by showing you some results that we've obtained with one of our customers. So starting with the technology that we're going to use for running our automatic checks, it's formal technology. As you know, in the olden days, formal technology was still the realm of engineers that hold math PhDs, and so they had to go and create their own programs to perform model checking. But that's changed in the 90s and 2000s, where formal property checking has taken off, and pioneers such as OneSpin have come up with tools that can easily allow you to write assertions and verify them. Still, you needed to have a lot of expertise to apply that to a complicated electronics design. However, what's driving a wide adoption of formal technology over the last 10 years are the advent of automated formal apps. So these are essentially apps within your formal property checking tools that alleviate the need for writing the assertions in the first place. The apps will go and create the checks automatically for you, and that basically takes formal into the hands of all verification engineers, and in a way democratizes formal and drive growth. And so we see a wide adoption, not least because it is now easier to deploy formal, but also many ASICs require 2 or more respins, making the justification for using formal a necessity in any project. One of those apps is Advanced Linting App, or auto checks as we call them in the Questa OneSpin Solutions product. So they're very, very easy to deploy because you can start early verification of your RTL without the need for any test bench and without the need to create assertions. As I said, the tools would create that for you. So you take RTL, push it through the tool like DV Inspect, and that can generate results for you fairly quickly. And you can catch a broad range of issues using these linting auto checks based on formal technology. They can be as simple as easy lint type of checks, so they rely on structures. So the minute you read in RTL, we can check mismatches in width of ports, of connections. We can check whether signals have been truncated or signals that may not have any load, any sync. You can check things like sensitivity list issues, which may be incomplete, and use signals and use parameters and so on. Of more value, you can also run safety checks. They require the creation of assertions, and this is what the magic of the tool does, it creates those assertions. With this, you can catch safety and functionality type of issues, such as runtime errors. So you don't want to have array index out of bound or range that is not valid, which will show at some point in simulation, but in formal, you can catch it fairly quickly. Similarly, you can do things like checking functions that can execute without returning a value or a signal that gets out of its intended domain. You may check for simulation synthesis issue like full case, parallel case, or you can look for arithmetic type of checks, such as do you ever have a situation where you can divide by 0, you may have negative exponents, negative reminders, you may have arithmetic overflow, and so on. All of which, as I said, can be caught in simulation, but is much more productive to catch using advanced linting based on formal. Probably the most popular of the application of auto checks is reachability and reachability analysis, which relate to how the design can be activating and what type of coverage you can achieve on it. And so dead code checks are very, very popular as part of an advanced linting strategy. Simply by connecting the design together, you may render some of the logic in the design as unreachable. So you don't want to waste a lot of time in simulation trying to hit it, and the tools can generate checks for that. In the same way, you can come up with toggle tests to see whether the integration of certain blocks cause some of the internal pins not to toggle any further, whether that's intended or not. And for FSM, you're looking at whether all of the states are reachable and all of the transitions of those states are reachable. The auto checks give you this ability to run all of these good checks. You also have the ability to debug these issues in a waveform viewer, much the same as you would do in a simulation environment. So you've got a waveform with measurement tools, and it's context sensitive depending on the auto check that you're running. So if it's an FSM, it'll come up with a table with all the appropriate transition tables with all of the appropriate states, and show you what's possible to reach, what isn't possible to reach. As you'd expect, it's a fully fledged debugger, and therefore you'll have a waveform viewer, and you can cross-probe into the source code, you can annotate, and so on. All this is good. Many of our customers ask, this is so useful that it allows us to catch so many issues, we'd like it to be part of a continuous integration flow. Essentially, as you go through RTL code churn, you're adding functionality, you're fixing some other issues, you want to make sure that the RTL stays clean. Continuous integration is part of many organizations' design and verification strategy that allows them to automatically build a design, run some verifications on it, and generate status and decide on what action to take based on the checks that they have achieved on it. Auto checks or formal linting is actually ideal for including as part of a continuous integration flow, because there is no manual intervention needed. All you need is the RTL that needs to be read in the tool. And so it's high value in detecting these RTL issues, but many users are put off because they say, hey, but this is formal. And is it going to take too long? Will it actually converge on all of the checks? Do I need to add some constraints so that I get the appropriate results and I find the root cause of the issues. And so here are some considerations for how you can come up with tests that fit into your continuous integration flow. So much like you'd have a regression tailored for continuous integration flow for your simulation, for example, using Questa Sim, you can also have a set of tailored customized auto checks that you could run in Questa OneSpin that also contribute to a DevOps pipeline. In simulation, you may be using test grading to pick the best test to run for a minimum regression that you could run, for example, daily or over the weekend. For auto checks, you need to consider different prioritization techniques. And so the common criteria for choosing a regularly scheduled auto check are going to be slightly different. First, you may be looking at how good the quality of the check is. So what is the severity of the failure? So is it going to be a fatal for the design, for example, an out of bound? Is it going to cause a simulation synthesis mismatch? Is it an FSM deadlog analysis? All of which are very high value. Lower value type of checks could be just initialization or all of the registers initialized. But you also have to consider the runtime. Deadlock analysis may well take longer than initialization checks. You may also want to prioritize based on accuracy. So is there a low chance of a false negative? In other words, are you sure that without any constraints, you will actually find failures such that you don't have to intervene and add any more constraints later when you found a particular failure? And all of this depending on the end use. So who's going to be running these jobs? Is it a designer? Is it a verification engineer, a QA engineer? Or is this something for management to track progress? And so based on this, you might want to go and study the auto checks that you run on a design and come up with an optimal order to perform the auto checks. So you could order them in higher value, lower runtime. These are the best to run. Obviously, the lower value, the higher runtime are the worst to run as part of a continuous integration flow. Based on that, you can come up with a greater granularity, so high value, low runtime, for example. FSM checks are of high value. Whether they are reachable is low runtime. Of medium value, you may be looking at transitions and so on. Low value, high runtime could be like, for example, toggle checks on some internal things that may actually require some configuration to be constrained to put them in that configuration. And so you'd come up with a list based on this prioritization, and you'll consider the end use. So if it's a design engineer, you may be wanting to include logical coding bags type of checks. The design engineer is going to be interested in handing over clean RTL to the verification engineer. Similarly, a verification engineer may be looking at integration bags, checking the functionality of each subcomponent. A manager, for example, would be interested in checking progress, trend versus time scales, and the type of issues that are found. So going through this, you'd come up with a set of tests. They could be sanity type of test or deep verification type of test, or you may be targeting a special area, running SOAK, for example, type of test. Sanity, it's probably high value, fairly low runtime, whereas targeted, it's high value, medium value, but you probably should be prepared to run the tool for longer. In Siemens, we have customized our tools such that we provide you with these techniques as a set of procedures, which we call quick, lunch, night, weekend. So we've already fine-tuned the engines so that we can run them fairly quickly and find high value with low runtime checks. You could run something over lunch for 1 hour, or you could run something overnight, 12 hours, or let it run over the weekend, 48 hours, enabling more checks, but also allowing for more runtime. And these will all include time limits, so they can be customized and they're provided to you as a procedure to customize it for your own need. So once you've come up with this, you want to take this to Jenkins. So Jenkins is a very popular source Java tool. What does it need? Well, it needs some regression data, and based on that, it generates reports. The Jenkins flow allows you to schedule batch jobs. You need to create plugins to collect the results, to create the reports, and generate debug traces so that the engineers can debug them. And here you've got a set of APIs available to you, so you can customize the reports or run a choice of quick lunch, night, weekend jobs. What's needed? CSV file is needed that contains the information to be analyzed. You can generate that from our tool, much the same way that if you're doing for simulation, you probably need the coverage database. Here's an example of the customization commands that you could use within OneSpin to get the text that you need, either report result, which is high level, generate sign-up information, or get consistency info, which is a typical procedure for generation, for example, the branch path, the instance name, the module name, and our customers use them to generate the report they need. One of our customers did exactly that and built a sanitization Jenkins flow. They check the setup is correct, they check for dead code, they check for model building issues, and these are the tests that they come up with to run in their Jenkins sanity procedure. The array index, no return, and so on and so on. Summary, formal analysis verification techniques do add value to continuous integration flow. And Questa OneSpin solutions provide automated checks that can easily fit into continuous integration flow. We provide an API and we provide Jenkins plugin templates that can help you use as a starting point for your own continuous integration. Thank you.
Thanks, Yassine. Thank you very much. Hopefully you can hear me.
I can hear you indeed. Thank you.
So we've got a couple of questions online. So the first one is regarding how long does it typically take to set this up? So if I was starting from completely from a fresh, no formal verification experience, how long do you think this would take me to set up inside the?
So I can interpret the question into two ways. How long does it set up? Auto checks in OneSpin, that's very, very minimal setup. You just need to read RTL in. As long as the RTL is suitable for formal linting, we can get you started in a couple of hours. How long does it take to create a plugin for Jenkins such that I can run auto checks as part of my continuous integration flow? That is going to be variable. It very much depends on the kind of reporting that you want to extract from the tool. If you're going to use the report commands that are already available in OneSpin, then again, that you should be able to get this done in a couple of days. Okay. If it's something much more customized than that, then you probably need to use the API, and it depends on what that information is.
Okay, thank you. Another question. Can you use the output of reachability test to feed into a simulator of choice? Does it have to be Questa?
Yeah, so it's a question that is not necessarily related to continuous integration. Yes, in the case of OneSpin, we generate waiver files that are text files, which can be read from all of the available simulators out there. So Questa is one of them, but the others are also supported.
Okay, thank you. And the last question is, someone's asked very specifically where they can find more details or information for the types of scripts or sample projects. This can show the whole CI flow.
Yeah, so please do get in touch.
Okay.
and we can work with you. Yeah, we get in touch with me, and we can work with the appropriate.
So the best thing is to get in touch with you directly, and then you can supply them. Okay, good answers, and thank you very much. It's good to see formal entering into the mainstream. More power to that, I think. Thank you very much. Okay, thank you, Yassine.
Thanks, Mike.
Thank you, Yassine.